In this video, we'll be having our second half of our chapter 10 lecture, that is for chemical bonding. So what we had in our first lecture was that we went over bonding theories and Lewis dot structures. We went over Lewis dot structures of atoms, of ionic compounds, and of covalent compounds. And of those covalent compounds, we can have some compounds that are polyatomic ions. If we have a polyatomic ion, we have to take into account the charge of our ion in terms of determining how many valence electrons we have. In this lecture, we'll be looking at geometries, specifically electron group, or sometimes called electron domain geometries, and the molecular geometries. We'll also briefly be looking at electronegativities of our different atoms, and how the geometries and the electronegativities determine whether a molecule is polar or nonpolar. So when we're predicting the three-dimensional shape of a molecule, we'll use the Lewis dot structure that we learned previously, and then we'll combine this with the valence shell electron pair repulsion theory, which is known as a VSEPR theory. The valence shell electron pair theory, or pair repulsion theory, is essentially taking into account that different electron groups or electron domains will repel each other. Therefore, these different electron groups will want to be as far apart as possible. We know that negative and negative charges, just like in magnets, will actually repel each other. For the same reason, these electron groups will repel each other. Now, these electron groups can be lone pairs, single bonds, double bonds, and triple bonds. Whether you have some lone pairs, some single bonds, some double bonds, or triple bonds in your structure, each one of these actually are considered one electron group. So for example, if you had a central atom, let's call it X, and let's say that it had around it, after you drew the Lewis structure, we saw that it had around it a lone pair of electrons. It also had a single bond to, let's say, atom Y, and then it also had a double bond to atom Z. What we see is that around our central atom, we have one lone pair, so that's one electron group. We have a single bond here, which is another electron group, and we have a double bond here, which is another electron group. So in total, we have 1, 2, 3 electron groups here. Now, what we see in most of our chemistry classes is that we see typically anywhere from 2, 3, 4, 5, or 6 electron groups around our central atom. We will be studying each one of these in this part of the video, but our more focus will be on when we have 2, 3, and 4 electron groups. Now let's look at when we have our more basic geometries. So that is when we have anywhere from 2, 3, and 4 electron domains around our central atom. So I will be showing this to you by using marshmallows and toothpicks. Let's imagine in the first case, we have 2 electron domains. This is our central atom. Around our central atom, we'll have our different electron domains, which is what I use here as our toothpicks. Our toothpicks will represent our different electron domains. And we will want these electron domains to be spaced as far apart as possible around our central atom. So if we have 2 electron domains, and we want to space them as far apart as possible, say we have one here, in order to space it as far apart as possible, we'll have the other one on exactly the opposite side. So in total, we have 180 degrees difference between our electron domains. In order for this to be considered a central atom, our electron domains in this case both have to be bonding domains, whether those are single bonds, double bonds, or triple bonds. For both our electron domain geometry and our molecular geometry, because both of them consist of two bonding domains, this forms a linear shape. So we call the electron domain geometry linear, and we also call the molecular geometry linear. Now, in the case that we have our central atom, but it actually has 3 electron domains, we'll want to space these electron domains as far apart as possible. So if we have one here, and I would try this out for yourself using things that you have at home, whether they're food items like this or possibly putty if you have it at home. In order to space them as far apart as possible and give them the same distance from each other, we form a geometry that looks like this. Now we see that this has all of the electron domains, or let's say that all of these are bonds in this case. All of the bonds in this case are along one plane. So for the electron domain geometry, whether some of these are lone pairs, others are bonds, or all of them are bonds, we call this trigonal because it has 3 portions to it. So trigonal planar because it's along one plane. Now let's imagine that after we drew the Lewis dot structure, we saw that the electron domain geometry was trigonal. So if we add up all of the bonding domains plus the electron pairs, and we have 3 electron domains total, then we have electron domain geometry of trigonal planar. But now let's imagine that after we drew our Lewis structure, we saw that one of our electron domains was actually an electron pair. So if one of them was an electron pair, let's just cover up the electron pair and see what shape is left by what is made out of our bonding domains. So if I was to use this as an example, we have a rod. If I was to bend it right in the middle, we see that if I was to cover up the top electron domain, because we're saying that it is a lone pair, these shapes are identical to each other. And this shape, by bending it, we'll call this shape bent. So the molecular domain geometry, in the case that there's 3 electron domains, but one of them is a lone pair, so we only have 2 bonding domains, the molecular geometry is then called bent. Now let's look at if we had 4 electron domains around our central atom. So if we had 4 electron domains, at first thought, we will probably want to arrange our different electron domains along a 2-dimensional structure. We see here that each of our electron domains is actually separated by 90 degrees. But what we have to remember is that our actual geometries can be 3-dimensional. So if we rearrange these, so we have our 4 electron domains, and we want these to be as far apart from each other as possible. We can actually arrange them to have further separation between each of our our different electron domains. In this case, the distance between each of our electron domains, or the angle between each of the electron domains, is 109.5 degrees, which is a further separation than the 90 degrees we saw in the two-dimensional structure. Now, if all four of these, or when we have 4 electron domains, what we call this shape is tetrahedral. And if all 4 of these electron domains are molecular domains, so that they're all bonding domains, then we can call the molecular geometry also tetrahedral. Now let's imagine we had the 4 electron domains, but that one of our electron domains is actually a lone pair. Remember, we would see this after we draw the Lewis structure. Now we want to describe the geometry that's left between our different bonding domains. What we see is this forms what is like a 3-sided pyramid. So we would call this shape trigonal pyramidal. That would be the shape of the molecular geometry when we have 4 electron domains, but one of the electron domains is a lone pair. Now let's imagine we had 4 electron domains, but we had 2 of the electron domains be lone pairs. So I'm going to go ahead and cover up this back electron domain and the top electron domain to look at the geometry that's actually formed between our bonding domains. So our bonding domain geometry, or molecular geometry, now looks like what we had seen earlier. We can call this shape a bent shape. So when we have 4 electron domains, but 2 of them are our lone pairs, we see we have a bent molecular geometry. So what we just looked at was when we had 2, 3, and 4 electron groups. And we see that the electron domain geometry, when we have 2 electron domains, is a linear geometry, and they have 180-degree separation between the 2 electron domains. When we have 3 electron domains around our central atom, we have a trigonal planar geometry, and their separation is 120. Notice that 120 plus 120 plus 120 equals 360, because this is all along one plane. In the case of when we have 4 electron domain, we have a separation between these different domains by a distance or an angle of 109.5. Remember that we want to always have our electron domains as far apart as possible, because these electron domains will repel each other. Now, when we're predicting the shapes of molecules, the first thing we need to do is draw the Lewis electron dot structure, which is in the earlier video for this chapter. Then we want to look at the electron domains that are directly around the central atom to determine the electron domain geometry. Remember that the electron domains will be arranged in order to minimize the repulsions between the electron domains. That is, that we'll want the furthest separation. After we have our electron domain geometry, we then cover up the electron pairs to see what the bonding domains make for their molecular geometry. Let's see for CO2 what the electron domain geometry and the molecular geometry is. So the first thing we need to do is we would need to draw out the Lewis dot structure for our molecule here. We know that carbon is going to be our central atom because it is the least electronegative. After we draw out all of our valence electrons and make sure that each one of our atoms has an octet and that we use up all of our valence electrons, we see that this is the Lewis dot structure for CO2. we saw before that when we have two electron domains, the furthest separation between these two electron domains is when we have 180 degrees separation. That is that they are completely oppositely arranged around our central atom. So our electron domain geometry will be linear. And because in the case when we have a central atom with two electron domains, both of those electron domains have to be bonding domains in this case. So our molecular geometry would also be called linear. If we were to draw the Lewis structure for a different compound, H2CO, we know that hydrogen is actually our least electronegative, but hydrogen cannot be our central atom because hydrogen can only hold up to two atoms, or two electrons, I'm sorry. So it can only have a duet of electrons. And out of carbon and oxygen, carbon is the least electronegative. So carbon will be our central atom. After we draw out the Lewis structure to all of our terminal atoms, we see that we get this shape. So in total, we have 1, 2, 3 electron domains around our central atom. So the electron domain shape is called trigonal planar because it has 3 electron domains around our central atom. And we said that these 3 electron domains will all be arranged in one plane. Now, if all of these electron domains are bonding domains, we call the bonding or the molecular geometry also trigonal planar. Notice in this case, because not all of our bonds are identical, we have bonds to different types of atoms in this case. We actually don't have exactly 120 degree separation between each of our bonds. Our double bond will actually have greater electron density around it, so it'll push away those single bonds further away from itself. So what will happen is that the bond angle between our oxygen, carbon, hydrogen, that bond angle is actually going to be a little bit larger than 120. Specifically in this molecule is found to be 122. In this case, we would have the same bond angle. And so the bond angle between our single bonds will therefore be 116, because at the end, this is still a planar structure along one plane because it's a trigonal planar structure. And at the end, all of these different bond angles have to sum up and equal 360 degrees. Now let's see if we have a structure that ends up having 4 electron groups. So if we were to draw out the structure for CH4, by the way, this is a typo, this should say CH4. If we're to draw out CH4, the Lewis structure for it, which we did in the first video, we see that the Lewis structure looks like this, and we have 1, 2, 3, 4 electron domains around the central atom. We saw earlier that when we have 4 electron domains, we're actually going to arrange those different electron domains in a 3-dimensional structure so that we end up having 109.5 degrees separation between each of our bonds or our bonding domains. In this case, all 4 of our electron domains are bonding domains, so the molecular geometry as well as the electron domain geometry are called tetrahedral. But in the case of NH3, when we draw NH3, the Lewis structure shows that we still have 1, 2, 3, 4 electron domains. So the electron domain geometry is still going to be a tetrahedral geometry. But when we ignore the contribution that's coming from the contribution of the shape that's coming from the electron pair and only look at the shape that's coming from our bonding domains, we call that a trigonal pyramidal because it's a three-sided pyramid. So the molecular geometry will be called trigonal pyramidal when we have 4 electron domains, but one of those electron domains is a lone pair. So similar to how we saw that the double bond will push away the single bonds a little bit further from itself, a lone pair will do something similar. So the lone pair here will actually push these single bonds or these other bonding domains further away from itself. So the bond angle between one bond to another bond is actually going to be a little bit less than 109.5. Specifically, when we have one electron pair that's pushing the other bonding domains away from itself, the bond angle ends up being 107 degrees. When we draw the Lewis structure for H2O, we find that oxygen is a central atom, and it has 2 bonds and 2 lone pairs. So in all, it has 1, 2, 3, 4 electron domains. So the electron domain geometry, if it has 4 electron domains, is still going to be a tetrahedral electron domain geometry. But when we cover up the contribution that's coming from the electron pairs and only look at the shape that's formed from the bonding domains, we call this shape bent. Now we saw with NH3 that the lone pair pushed the bonding domains further away from itself. In the case when we have 2 electron pairs, they push the bonding domains even a little bit further away from both of those lone pairs. So the bond angle between the 2 bonding domains, therefore, ends up being a little bit less than what we saw with NH3. With NH3, with 1 lone pair, it was 107 degrees. In the case where we have 2 lone pairs out of our 4 electron domains, our bond angle ends up being closer to 104.5 degrees. This figure 10.2 shows the arrangement of electron pairs around an atom. So in this case, if we're just looking at electron pairs or electron domains, we see that our electron domain geometry is called linear with 2 electron domains, is called trigonal planar with 3 electron domains, and is called tetrahedral with 4 electron domains. In the case where we have 5 electron domains, it's actually called trigonal bipyramidal. What we see is that along one plane here in the center, we have 3 of our electron domains. And then right on top and right on bottom, we have the other 2 electron domains. Along each one of these planes, we form a 3-sided pyramid on top, and the same thing, a 3-sided pyramid on bottom. Therefore, we call it trigonal bipyramidal. In the case where we have 6 electron domains, we will have 4 in one plane and 1 on top and 1 on bottom. The angle between each one of these electron domains will be 90 degrees. We call this an octahedral electron domain geometry when we have 6 electron domains. By the way, when we have 5 electron domains, if we have 3 electron domains in one plane, then the angle difference is going to be 120 degrees between those bonding domains. That's all along one plane here. And the bond angle from that top electron domain to the one that's actually in the axes going into the paper or your computer, that's actually 90 degrees. So we see 2 different bond angles here. Overall, this is looking at what we looked at with looking at the marshmallows and our toothpicks. When we have 2 electron domains, both those electron domains or electron groups have to be our bonding domains. And in that case, both the electron geometry and the molecular geometry is called linear, and the angle is 180 degrees between our different bonding domains. When we have 3 electron domains, we can have all 3 of those electron domains be bonding domains, or we can have it so that only 2 of those electron domains are bonding domains and the other one is a lone pair. In the case that we have all 3 electron domains be bonding domains, we have the electron geometry and the molecular geometry to be called trigonoplanar. And if we have our 3 different bonding domains in one plane, the angle difference between our different bonds is going to be 120 degrees. When we have 3 electron domains, we can also have it that we have 2 bonding domains out of that and 1 lone pair out of that. In that case, we have a trigonoplanar electron geometry, so that's the same as before because that's based only on the number of electron domains. But our molecular geometry is going to be called bent. And in that case, our angle is a little bit less than 120, but it's going to be just less than 120. When we have 4 electron domains, we have 3 possibilities. One is when all 4 electron domains are bonding domains. One is where 3 of the electron domains are bonding domains and 1 is a lone pair. And then where we have 2 of the electron domains be bonding domains and the other 2 are lone pairs. In the case where we have all 4 electron domains be bonding domains, both of the geometries are called tetrahedral, and we have 109.5 degrees separation between our different bonding domains. In the case where we have 3 out of the 4 electron domains are actually bonding domains and 1 is a lone pair, our electron domain geometry is still tetrahedral, but now our molecular geometry will be called trigonopyramidal, and the angle will be a little bit less actually than 109.5. As we said before, it'll be closer to 107 degrees between our actual bonding domains. And in the case where we have 2 bonding domains and 2 lone pairs, the electron domain geometry is still called tetrahedral because it's still 4 electron domains overall. But when we only have 2 out of those 4 are actually coming from bonding domains, we call the molecular geometry bent. And the bond angle reduces a little bit more now than the 109.5 degrees. It is now going to be an angle of 104.5 degrees. And remember that this angle is between your different bonding domains. So we've learned how to draw the Lewis structure, the Lewis dot structure in 2D. That is, even for when we have 4 electron domains, we so far have learned how to draw them in a 2-dimensional type structure. But when we actually want to show the 3 dimensions of some of our geometries, we can do so by using hashed lines and wedges. Whenever we have hashed lines, that means that that bond is projecting a little bit into the board or a little bit into the plane of your computer in this case. And when we have a wedge, that's showing that that bond is coming a little bit out of the board or of your plane of your computer. Now let's look at electronegativity and polarity. So for example, why oil and water do not actually mix and they actually separate when you combine the two. This has to do with the polarity. Oil ends up being nonpolar and water ends up being polar. In this case, like dissolves like. So if we have a non-polar mix or a compound with another non-polar compound, they will actually dissolve into each other. If we have a polar compound and another polar compound, they will dissolve into each other. But if we have a non-polar compound and a polar compound, they will actually separate from each other, which is in the case of this. We have our non-polar oil separating from the polar water. Now, in order for a molecule to be polar, there needs to be a difference between the electronegativity between the atoms. What we mean by the electronegativity is the ability of an atom or an element to attract electrons within the covalent bond. So for example, if we have part of our, let's look at H2O. Let's just draw the Lewis dot structure. Here, I'm not going to draw the two lone pairs on the central atom, just because it's not vital for what I'm about to show to you here. But it is important to know the geometry in determining whether a molecule is polar or nonpolar. But in this case, let's look only at one bond. What we see is that from our electronegativity chart is that oxygen is much more electronegative than hydrogen. If oxygen is much more electronegative, we can display that with a partial negative sign because it's going to attract the electrons in this bond more toward the oxygen. And the electrons in the bond are going to be a little bit less attracted to the partial positive hydrogen. That is the atom with the less electronegativity. So we can either draw out the dipole moments using the partial charges, or we can also use what is more like an arrow to show that the electrons are going a little bit closer, oops, that's an arrow, to the oxygen, and we'll end up with a little bit more of a partial positive charge at the hydrogen. Now let's look at a different way of what we just looked at between the two OH bonds in H2O. Because we know that the oxygen is more electronegative, it'll attract more electrons around itself. And the hydrogen is less electronegative, which is represented by the partial positive charge, because it has less of those electrons around itself. The result of this uneven electron sharing is what we call the dipole moment. And it's a separation of the charge within the bond. Now here is your electronegativity chart. There are different types of electronegativity chart, but this is another good depiction of it, where you see that the most electronegative of your atoms is your fluorine atom. And you reduce in electronegativity as you go to the bottom left. Now, when you're looking at each bond within a compound, you need to look at the difference of electronegativity between the two atoms that make up that bond. And that will tell you whether each bond is polar or nonpolar. When the electronegativity difference is anywhere from 0 to 0.04, then we consider that to be such a small amount of electronegativity difference. That means it's such a small amount of one of the atoms wanting the electrons more than the other atom that we don't really consider that to be a polar compound. But in this case, it's still coming from a pure covalent bond. So for example, Cl2. If we were to draw out Cl2, and then of course fill in the lone pairs around your terminal atoms, which are both of the chlorines, we would see here that we would have the same electronegativity toward this chlorine and the same electronegativity toward this chlorine. So overall, the difference between both of these chlorines is 0. But this is a covalent bond because we're sharing the electrons. Let's look at another example. Let's look at if we had our methane. That is when we have CH4. Now we need to see if we actually have between each of these bonds enough of electronegativity difference. If we were to go back to electronegativity chart, we would see that the carbon has electronegativity of 2.4 and the hydrogen has an electronegativity of 2.1. Now the difference between these two electronegativities, so if we subtract the smaller one from the larger one, we have a 0.3 electronegativity difference. That ends up being less than 0.4. So that means that there is not really a pull of the electrons from one atom more than from the other atom. So this is still a pure covalent bond, but we consider this a non-polar covalent bond. When we look at the difference in electronegativity between hydrogen and fluorine, if we look at the chart that we saw before, hydrogen and fluorine, after we draw the Lewis dot structure, looks like this with the electron domains, electron pairs around the fluorine. The fluorine has a electronegativity of 4.0, and hydrogen has electronegativity of 2.1. So the difference in electronegativity is equal to the 4.0 minus the 2.1, which is equal to 1.9. When it ends up falling between 0.4 and 2.0, we call that covalent bond. We would call that a polar covalent bond. So that is that the fluorine is attracting the electrons much more to itself than the hydrogen is. And then lastly, if we have a much, much larger difference in electronegativity, so if it's greater than 2.0, then in that case, we have an ionic bond. Because we see that as we have our metals end up being less electronegative, and they are bonded or ionically attracted to our non-metals, which end up having a higher electronegativity. And the difference between them, the electronegativities, will give 2.0 or higher. Now, when we're drawing out our Lewis dot structure, we need to draw out the Lewis dot structure for CO2 in this case. We have it drawn out to the right three-dimensional geometry. In this case, it is a two-dimensional geometry where both of our bonds are opposite to each other. What we see is that we do have electronegativity difference between our carbon and oxygen. So each one of these bonds are electronegative, or are polar, I'm sorry. And the oxygen has the greater electronegativity. So we would draw the arrow this way with our more positive charge on the carbon. The same thing on the opposite side. But because these are exactly opposite to each other, these charges, or these pull of electrons more toward the terminal atoms, overall for the molecule makes the molecule nonpolar because they cancel each other out. However, when we draw out the three-dimensional geometry for H2O, we have to remember what the actual geometry looks like. That is what the molecular geometry looks like. If we had not considered what the actual molecular geometry looks like, we might think that this geometry looks similar to this geometry. But what we know is that the hydrogens are not actually bonded right across from each other. They're actually at a bent angle. So we do have a polarity going toward the oxygen from the hydrogen here, and we have another similar polarity here, but these are not opposite to each other, so they don't cancel each other out. So for H2O, that is a polar molecule. So here's a summary of the same thing. When we have two identical polar bonds pointing in opposite directions, they'll cancel each other out, and we'll call the molecule nonpolar. When we have three identical polar bonds at 120 degrees opposite to each other, and each one of them have the same pole or the same dipole moment, each one of those bonds have the same dipole moment, they'll all cancel each other out, and the molecule will overall be nonpolar. In the case that we have four electron domains, or electron, in this case, they're all bonding domains, all of them, in this case, have the same type of bond, and so they all have the same type of dipole moment. In this case, they'll also all just cancel each other out. So this is also a nonpolar molecule. But let's say that this one of these electron domains is actually a lone pair. So that will form this geometry here. This is now our molecular geometry if one of our lone pairs, or one of our electron domains is actually a lone pair. In this case, we have the contribution of the three bonding domains having a dipole moment, but they do not have that fourth electron domain being the same dipole moment. In this case, these dipole moments will not cancel each other out. Therefore, the molecule is polar. All right, let's take some time and determine the electron geometry and the molecular geometry of each of these molecules, and determine if the molecule is polar or nonpolar. All right, I hope that we all got to try this out for ourselves. The first thing we needed to do was we need to draw out the Lewis dot structure. After we draw out the Lewis dot structure, we need to see how many electron domains there are around our central atom, and how many of those electron domains are molecular domains, to determine if our dipoles will actually cancel out or not. If they do not cancel out, we consider the molecule to be nonpolar. If they do cancel out, we consider the molecule to be polar. So for CBr4, our central atom is going to be carbon. First of all, we should have accounted for that this will end up with 32 valence electrons. So our central atom is carbon. If we have 4 single bonds first to our different bromines, and we draw out the rest of our electrons around our terminal atoms to give them an octet. We see that we've used up all 32 of our electrons, and all of our atoms, including the central atom, has an octet. We know that this actually forms a tetrahedral geometry, so this is incorrect the way it's drawn two-dimensionally, but this shows it actually forms a tetrahedral geometry. That is something more like this. And then looking at the polarity difference, we see that there's actually a greater than 0.4 difference between our different bonding, our different atoms in our bonds. So our polarity difference gives us that our electronegativity difference gives that each one of our bonds is a polar bond. But because each one of these bonds and the electron domain geometry actually cancel each other out, this would be a nonpolar molecule. Now let's look at number 2. First thing we want to do is we want to draw out the electron domain geometry. Carbon, in this case, has to be our central atom. To oxygen, single bond, and we have to do this with more practice of just knowing how to draw our Lewis dot structures. We saw here that we have 12 valence electrons. We have to have 2, 4 drawn on a terminal atom, and we have a total of 12 valence electrons. This actually forms a trigonal planar geometry because we have 3 electron domains. So that is that carbon to oxygen, single bonds to hydrogen, actually forms a trigonal planar geometry. If each of these groups, these bonding domains were identical, then these would all cancel each other out. The polarities would actually cancel each other out. In this case, however, the carbon to oxygen polarity difference is high. It's actually more electronegative. The oxygen is actually more electronegative. Between carbon and hydrogen, it's actually less than 0.4. Carbon is 2.4, hydrogen is 2.1. So electronegativity difference is not high enough to be considered a polar bond. So these actually do not cancel each other out with this. So this molecule overall is considered polar. Let's try for CS2. When we draw out the Lewis dot structure, we see that it comes out to this geometry, or this Lewis dot structure. And we use up all of the 16 valence electrons. We see that the electron domains are all bonding domains. So for both the electron domain geometry and the molecular geometry, they are linear. What we see is that we could have a polarity difference both ways going towards the sulfur, where the more electronegative atom is our sulfur, but both of these will cancel each other out. So we have one going this way and one going this way, and they cancel each other out. So overall, this molecule is a nonpolar. We draw out the Lewis dot structure for BH3. We end up with this Lewis dot structure. Remember that boron is not required to have an octet. Often it'll have just 6 electrons around it. So we end up with this geometry. the electron domain geometry is trigonal planar. And because all of our electron domains are bonds, the molecular domain the molecular geometry is also trigonal planar. So each one of these polarities are going to cancel each other out. So this is a nonpolar molecule. And lastly, let's look at NH3. When we draw out the Lewis dot structure, we see that we end up with one lone pair and 3 single bonds to hydrogen. We have to remember that this is not the actual geometry, because when we have 4 electron domains, we have a 3-dimensional geometry. So that is, we have something more like this. Each one of these nitrogen to hydrogen bonds will have a more electronegative end toward the oxygen. Toward the nitrogen. And because this lone pair here, all of these polar bonds do not cancel each other out. So overall, this molecule is polar. By the way, the electron domain geometry here with 4 electron domains is tetrahedral. And when we have 3 of those electron domains actually coming from bonding domains and 1 coming from a lone pair, the molecular geometry is our trigonal pyramidal. Now we've learned about how to see if something is polar or nonpolar. What's interesting is that the molecules that are within our soap actually have a polar head, so a polar end on one side, and a nonpolar end on the other side. The nonpolar end attracts to the grease that may be on our hands. Like we said before, like likes like. So the nonpolar end will attract to the nonpolar grease. And the polar end of our soap molecule will attract to the water. So the nonpolar tail will get together all of the grease that's on our hands. And when we wash it with water, wash the soap molecule plus the grease now with water, the polar water will attract to the polar end of our soap molecule in order to make sure that all of our soap molecules are removed from our skin. All right, in chapter 10, we went over bonding theories, Lewis dot structures of atoms, ionic compounds, and covalent compounds. In this second video here, we went over the different geometries, specifically the different electron group or electron domain geometries, and the molecular geometries. We also looked a little bit more into electronegativity and how we can use the geometries and electronegativity to determine if a molecule is polar.